17.6 Springs, hot springs, and geysers. Distinguish among springs, hot springs, and geysers. The phenomena described in this section often arouse people's curiosity and wonder. The fact that springs, hot springs, and geysers seem rather mysterious is not difficult to understand, for here is water, sometimes very hot water, flowing or spewing from the ground in all kinds of weather, in seemingly inexhaustible supply, but with no obvious source. Springs. Not until the middle of the 17th century did the French physicist Pierre Perrault invalidate the age-old assumption that precipitation could not adequately account for the amount of water emanating from springs and flowing in rivers. Over several years, Perrault computed the quantity of water that fell on France's Seine River basin. He then calculated the mean annual runoff by measuring the river's discharge. After allowing for the loss of water by evaporation, he showed that there was sufficient water remaining to feed the springs. Thanks to Perrault's pioneering efforts and the measurements by many afterward, we now know that the source of springs is water from the zone of saturation and that the ultimate source of this water is precipitation. Whenever the water table intersects Earth's surface, a natural outflow of groundwater results, and we call this a spring. Springs often form when an aquitard blocks the downward movement of groundwater and causes the water to move laterally. Where the permeable bed crops out, a spring results. Another example is illustrated in figure 17.16, which shows a perched water table intersecting a slope. Springs, however, are not confined to places where a perched water table creates a flow at the surface. Many geologic situations lead to the formation of springs because subsurface conditions vary greatly from place to place. Even in areas underlain by impermeable crystalline rocks, permeable zones may exist in the form of fractures or solution channels. If these openings fill with water and intersect the ground surface along a slope, a spring results, figure 17.20. Figure 17.20 Thunder Spring. A spring is a natural outflow of groundwater that occurs when the water table intersects the surface. Thunder Spring emerges from a deep joint and cave system in the Muaf limestone along the north rim of the Grand Canyon. Photo by Michael Collier. Hot springs. There is no universally accepted definition of hot spring. One frequently used definition is that the water in a hot spring is 6 degree, 9 degree C, 10 degree, 15 degree F, warmer than the mean annual air temperature for the locality where it occurs, figure 17.21. In the United States alone, there are more than 1,000 such springs. Figure 17.21 Hot spring. Many hot springs, including this one in Iceland, are associated with areas that have experienced recent igneous activity. Photo by Andre Hassan/Alamy Images. Temperatures in deep mines and oil wells usually rise with increasing depth, an average of about 25 degrees Celsius 45 degrees Fahrenheit per kilometer. You learned in Chapter 4 that this is called the geothermal gradient. Therefore, when groundwater circulates at great depths, it becomes heated. If the hot water rises rapidly to the surface, it may emerge as a hot spring. The water of some hot springs in the eastern United States is heated in this manner. The springs at Warm Springs, Georgia, the presidential retreat of Franklin Roosevelt, are one example. The temperature of these hot springs is always near 32 degrees Celsius 90 degrees Fahrenheit. At Hot Springs National Park, Arkansas, water temperatures average about 60 degrees Celsius 140 degrees Fahrenheit. The great majority, more than 95%, of the hot springs, and geysers, in the United States are found in the West. A glance at figure 17.22 reinforces this fact. This is because the heat sources for most hot springs are magma bodies and hot igneous rocks, and igneous activity has occurred more recently in the West than in the rest of the country. The hot springs and geysers of the Yellowstone region are well-known examples. Figure 17.22 Distribution of hot springs and geysers. Note the concentration in the West, where igneous activity has been most recent. Geysers. Geysers are intermittent hot springs or fountains in which columns of water are ejected with great force at various intervals, often rising 30 to 60 meters, 100 to 200 feet, into the air. After the jet of water ceases, a column of steam rushes out, usually with a thunderous roar. Perhaps the most famous geyser in the world is Old Faithful in Yellowstone National Park, figure 17.23. The great abundance, diversity, and spectacular nature of geysers and other thermal features in Yellowstone undoubtedly was the primary reason for its becoming the first national park in the United States. Geysers are also found in other parts of the world, notably New Zealand and Iceland. In fact, the Icelandic word geysa, meaning to gush, gives us the name geyser. Figure 17.23 Old Faithful. This geyser in Wyoming's Yellowstone National Park is one of the most famous in the world. Contrary to popular legend, it does not erupt every hour on the hour. Time spans between eruptions vary from about 65 minutes to more than 90 minutes and have generally increased over the years due to changes in the geyser's plumbing. Photo by Jeff Benuga/Corbis. How geysers work. Geysers occur where extensive underground chambers exist within hot igneous rocks. How they operate is shown in figure 17.24. As relatively cool groundwater enters these chambers, it is heated by the surrounding rock. At the bottom of the chambers, the water is under great pressure because of the weight of the overlying water. This great pressure prevents the water from boiling at the normal surface temperature of 100 degrees Celsius 212 degrees Fahrenheit. For example, water at the bottom of a 300-meter, 1,000-foot, water-filled chamber must attain nearly 230 degrees Celsius 450 degrees Fahrenheit before it will boil. The heating causes the water to expand, and as a result, some is forced out at the surface. This loss of water reduces the pressure on the remaining water in the chamber, which lowers the boiling point. A portion of the water deep within the chamber quickly turns to steam, and the geyser erupts. Following eruption, cool groundwater again seeps into the chamber, and the cycle begins anew. Smart figure 17.24. How a geyser works. A geyser can form if the underground plumbing does not allow heat to be readily distributed by convection. Tutorial. How a geyser works. Geyser Deposits. Your browser does.
Hello, this is Callan Bentley. Welcome back for another Smart Figure. After watching this video, you should be able to describe the sequence of events that have to take place in order for a geyser to erupt. A geyser is a special kind of hot spring, and this is a map showing the distribution of hot springs in the lower 48 United States. Alaska and Hawaii are not included here, but you can see there are clusters in western Virginia and eastern West Virginia, in Georgia, in Arkansas, and then basically through most of the American West. The reason that you see this big asymmetry between West and East is that the Western United States is tectonically much more active, and so there's a lot more faulting, a lot more fractures in the crust that are bringing hot water up to the surface, and also a lot more magmatism, a lot more volcanic activity. And you can see there's a particularly big cluster right at Yellowstone National Park. That's the greatest concentration of geothermal features anywhere in the world. So what has to happen for a geyser to erupt? A geyser is basically where hot water and steam suddenly erupt from the ground. Well, basically we have to have a situation where we've got a large chamber below the surface. You can see the water table here going across from left to right. And basically that chamber is subject to warming. So there's some amount of heat flow that's coming in from the surrounding crust. As it warms up, the bottom gets to the point where it is above the boiling temperature. So it's basically hot enough to boil, but it's under pressure from the overlying water. And so that means that the overlying water starts to heat up more and more and more. Until eventually what ends up happening is the top of that body of water in the subterranean cavern gets heated up to the boiling point, and there's no water over it. So it flashes to steam, and that releases the pressure on the water underneath it. It also flashes to steam, and that releases the pressure on the water underneath it. And so basically, in a chain reaction from top to bottom, suddenly this whole cavern evacuates itself by having the hot water turn to steam, and it expands rapidly, finding its way out at the surface, and that's the geyser eruption. What would be the next step in this sequence? Well, hopefully you would say that geysers don't just erupt a single time, they erupt repeatedly over time. So what we would expect to happen next is for water to flow back into this subterranean cavern from the surrounding rock. So leave the pore spaces of the surrounding rock and end up back filling this cavern. And then, of course, the heat can start being added to that, and the whole process can repeat itself. Nice work. Thanks for your attention, and this has been another Smart Figure.
Geyser Deposits. When groundwater from hot springs and geysers flows out at the surface, material in solution is often precipitated, producing an accumulation of chemical sedimentary rock. The material deposited at any given place commonly reflects the chemical makeup of the rock through which the water circulated. When the water contains dissolved silica, a material called siliceous sinter, or geyserite, is deposited around the spring. When the water contains dissolved calcium carbonate, a form of limestone called travertine, or calcareous tufa, is deposited. The latter term is used if the material is spongy and porous. The deposits at Mammoth Hot Springs in Yellowstone National Park are more spectacular than most others, figure 17.25. As the hot water flows upward through a series of channels and then out at the surface, the reduced pressure allows carbon dioxide to separate and escape from the water. The loss of carbon dioxide causes the water to become supersaturated with calcium carbonate, which then precipitates. In addition to